Okay, what we were doing. Please, can you tell me if you can see my OneNote page on your screens? Is it okay?
Yes.
Okay, thank you. Somehow I need this kind of verifications from you. Okay, so here is our next example. We will compute limits algebraically again, but this time we have an absolute sign function in our expression. Okay, whenever you have absolute sign in limiting questions, in limit questions, you need to divide it into two parts because you need the information that whether this expression inside your absolute sign is positive or negative to evaluate it, right? That's why we will look at one-sided limits. So limit of this expression as x goes to 0 from left or right, as x goes to 0 from right. Okay, we will look at these two one-sided limits. Okay, for the first one, if x goes to 0 from right, what happens? So 0 is here, and you are approaching from right. You are inserting kind of 0.00001 kind of numbers for x. So what do you think? Is this positive or negative, the expression inside absolute sign? Is it positive or negative? Obviously, since you are on the right side of
Positive.
the equation, it is positive. We need this information because we need to evaluate the absolute sign. Okay, since it is positive, now I am ready to evaluate the absolute sign function. Absolute sign of x is evaluated as just it is, right? Because the expression inside x is positive. That's why it is evaluated like this. After you evaluate absolute sign, you simplify x's and you end up with just 1 inside your limit expression. So the result is 1 in the first case. Okay, for the second case, where you approach 0 from left. In this case, you are approaching from left. That's why you will insert values like 0.0001, but minus of it, right? You are on the left side. That's why this is negative in this case. So if you want to evaluate this limit, you will do as x goes to 0 from left, x over, how do you evaluate absolute sign with a negative expression inside? You need to put an extra minus sign in front, right? This is how you evaluate absolute sign when the function is negative inside. So simplify and you end up with just -1 after you simplify. That's why the result is -1 in this case, okay? So if you compare the results, you see that they are not the same, okay? They are different. They are not the same. So how you conclude then about the overall limit of this function at x goes to 0 without any direction? So what do you think? What is this limit? Since one-sided limits are different, one of them is 1, one of them is -1. Since they are different, limit does not exist. Okay? So that's how you should treat the limit exercises, including absolute signs. You need to look at one-sided limits and verify whether they are equal or not. Now look at this one. Again, for this question, we will look at one-sided limits too, because, okay, let me show you. As x goes to 1 from right, and we will also look at as x goes to 1 from left. If you are on the right side of 1, you are approaching from right, you will insert something like 1.00001. If you insert x as this number, this, and subtract 1 from it, is this part, what is this difference then? If x is such a number, you will find 0.0001 or something, right? And when x goes to more closer and closer to 1, this difference will get more closer to 0. So the result is in fact kind of 1 over 0, which is, what is 1 over 0?
Infinity.
It is infinite. So you will think like, okay, if you divide 1 with this very, 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 very small number, you will find something huge, very big, right? If it becomes exactly 0, it diverges to infinity. It is the infinite value. So maybe it's a good idea to put a recall here about such ratios. So you may want to use sometimes 1 over 0, sometimes it will be 0 over 1, sometimes we will deal with infinity over 0 or 0 over infinity. So you need to know the results of such ratios. 1 over 0 is infinite. 0 over 1 is what? It is 0. Infinite over 0 is obviously infinite because instead of 1, you write infinite, which is much more bigger than this. So infinite. 0 over infinite is 0. Okay, don't forget such expressions. Now, we can turn back to our exercise. In the second part, we are approaching 1 from left, from this direction. This time, I'm inserting 0.999 kind of number. If you insert this number to x here and subtract 1 from it, what you will obtain at the denominator? Okay, this difference will become like minus 0.001 or something, right? Because, you know, you are on the left side, you subtract 1, which is a bigger value, so you will obtain a minus. Then, what do you think is the result for this case? You are dividing 1 with a very small number again, but which is negative. Okay? This is now negative. That's why you will obtain a very big number, like infinity, but this time it will be minus infinite as the value on the denominator is negative. Okay? So it is like that. That's why now we will compare them to give the overall result. Then what about the limit of the given function as x goes to 1 without any direction? What do you think? They are different, so this limit does not exist. Okay. So let's move on, if no other questions about this part. Okay, I move on. This is a very nice exercise, which is kind of famous. Again, you can find lots of YouTube videos on this exercise, and of which I covered in my lecture video too. Maybe we can recall something from the lecture videos. Okay, let's recall this function. F of x is sine 1 over x. This is a famous function which behaves like, okay, obviously since it's a sine function, it will take values between +1 and -1. This is obvious because it is sine. But its behavior is a bit strange. Okay, it oscillates. It's an oscillating function, but oscillations get more frequent as you approach the origin. It gets more frequent, and around origin, it behaves like crazy. Like there are infinitely many oscillations at origin, okay? I cannot draw it, but I can describe it to you. Then it oscillates back to normal, like in normal frequencies, but around origin, it oscillates infinitely many times as it is seen here, okay? I'm sorry, I couldn't draw it nicely, but you understand what I mean. There are infinitely many oscillations here, and then it goes back to normal behavior. Then, now I want to compute the limit of this function as x goes to 0 around origin. What do you think? So there is a crazy behavior here. There is a wild oscillation. meaning that there are infinitely many oscillations around origin. So, is there any unique number around origin to which this graph approaches? What do you think? Infinitely many oscillations around origin. This describes the behavior of this function. There is a wild oscillation around x equals 0. So what do you think? Does this limit exist? Can you please share your comments with me? Since there is infinitely many oscillation here, there is no unique number to which this function approaches. It is impossible, right? At 1 second, the values are very close to 1. At the next second, they are very close to -1 because of this crazy behavior here, because of this infinitely many oscillations here. That's why, as I said, there is no unique number to which. So let me first write my explanation, then you will give me the result. This function, it oscillates too fast that there is no unique real number to which the values approach. So, okay, let me finish my sentence. Approach. You understand this wild behavior, I guess. Since there is no such real number because of infinitely many oscillations, limit does not exist for this function, okay? So this is the explanation. This is already covered in the lecture video. Now let's look at our function. It is a bit different. Our function is defined as this function on the right side of the origin, and it is defined as 0 on the left side. Now we will look at all those questions. First of all, we want to answer one-sided limits. Limit of f of x as x goes to 0 from right. As I explained, on the right side, there are infinitely many oscillations, just like here. The only difference is just you are looking at from the right. This limit does not exist because of this crazy behavior around the origin on the right side. The explanation is the same. There are infinitely many oscillations, no unique number towards which your values can approach. Okay, part B. Limit of this function as x goes to 0 from left. This time you will look at from the left direction, okay, from left. And on the left, your function is defined as a constant function. The values are approaching towards, obviously, 0 because it is constant function 0. From the left, limit exists. Now, what about overall limit? On one side, limit does not exist. On the other side, limit exists as 0. Then this overall limit, what do you say? What is it? You will just compare these two, right? They are not the same. One-sided are not the same. That's why limit does not exist. Okay, if you compare the one-sided limits, since they are not the same, limit does not exist. Okay. Any questions about this solution now?
No.
Okay, you are so silent today, which is not good for all of us. Okay, let's move on. Now we will deal with this group where some one-sided limit computations are given. So these are algebraic computations. For example, for this one and this one, I think I already explained what to do in the first lecture. So what you are supposed to do for these two? Who remembers from the first part?
Multiply by conjugate.
Exactly. You see, you have these square root functions. This is a very strong indication that you will divide and multiply it by the conjugate of it, of this expression. So I write the same expression, I will just change the sign, okay? This is the conjugate of it. You will multiply, also you will divide by it, not to change the question. I won't do the whole computation. This is now a minus b, a plus b form. You will multiply and then you will start having simplifications and you will obtain your result. This is very similar, multiply and divide by the conjugate. Okay, let me choose some from one of these parts because these are similar as they all contain absolute sign, and I explained here how to deal with absolute signs, right? You will look at one-sided limits to evaluate the absolute sign by looking at the functions being positive or negative, okay? That's the only way to evaluate the absolute sign. You need to know the sign of the insider function, okay? So let's choose this. Okay, this one. Sorry, this one. Limit x plus 3, x plus 2, absolute sign x plus 2 as x goes to minus 2 from left. Okay, this is your minus 2 point and you are approaching from left. So you are inserting kind of minus 2.0001 kind of numbers, right? And then you add plus 2 to it. Then what is the sign of this expression?
Minus.
Exactly. So if you choose x as minus 2.0001 kind of numbers from left direction of minus 2, this thing inside will be negative. That's why now you are ready to evaluate absolute sign. How you will evaluate it? You will remove it, but you need to put this extra minus sign in front because it's a negative function. So minus of it. Then you are ready to compute your limit after evaluating the absolute sign. So minus x plus 2 divided by x plus 2. You know, this is a simplification now. And you end up with this limit question minus this as x goes to minus 2. Now you are safe to insert minus 2. Okay? So the result is minus 1. But why we are not safe at the beginning to insert minus 2? Because since you haven't simplified yet at the beginning, since you didn't evaluate the absolute sign yet, you cannot simplify these two. And if you try to insert minus 2, you will obtain 0 over 0, which is an indeterminate form. To get rid of this indeterminate form, you need to evaluate absolute sign by looking at this direction and by deciding the negative or being negative or positive of the expression. It is negative, so we put an extra minus sign in front of it. Then you simplify and then you are safe to insert your number to obtain your result. Okay? So that's it. If you have absolute sign functions in your expression, which we all have in this group, you need to evaluate absolute sign correctly by looking at the sign of insider function. Okay, any questions? If not, I move on. Okay, I will leave this one as an exercise for you. You will try it by yourself, and if you have questions about it, you can ask to our assistant Mehmet Emin or to me. Okay, so you need to get your hands dirty to learn math. You know, you cannot learn mathematics or calculus course by just reading the solutions or by just listening to them. You need to get action. You need to start solving questions by yourself. Okay, this is also an exercise for you. Let me see. And I will continue with this one. This question covers another topic that I mentioned in my lecture videos, which is sandwich theorem. Okay. This is an important theorem. Let me remind it to you. Now, I will draw three different functions. Let's say this is h of x, and let's say this is f of x, and let's say this is our g of x function. As you can see from their graphs, there is an ordering between these three functions. Which one is the biggest one? H of x is the biggest function. Which one is the smallest one? G of x is the smallest, and f of x is the middle function. So from the graph of these functions, we see that h of x is the biggest one, g of x is the smallest one. So we have this ordering. Once you have such ordering between your functions, and if you want to compute the limit of the middle function, what you should do by sandwich theorem is you will look at the limit as, okay, let's say this number is a. As x goes to a, this is another notation for computing the limit. As x goes to a, g of x goes to which number? So you see that this dot is common for all of them, and let's say this is the real value L on y-axis. Okay, so the values of g of x approaches to which value on y-axis as x goes to a? They are approaching to this value L, right? And the same is true for h of x. So we are approaching from both sides to a, and the values of h of x are approaching also to L. If this is the case where smaller and the bigger function are approaching to the same real number, then the middle function has to have the same limit as x goes to a, and this is what we call as the sandwich theorem, okay? So this is how we will use sandwich theorem in our computations. And it is also obvious from the graph. You see that the values of f of x at a are kind of squeezed between h of x and g of x. The h of x and g of x force the function f of x to have the value L around a, okay? And this is the algebraic written version of it. Okay, if no questions about the theorem, let me solve this exercise for you. So you see there is an ordering here between the functions. And this is given as, the functions are given. This is g of x, smaller function. This is middle function f of x, and this is the bigger function h of x. And you see, we want to find the limit of the middle function as x goes to 0. Let me rewrite this inequalities again to here. X times sine x, 2 minus 2 cosine x, like that. Okay, so sandwich theorem tells us what? Just look at the limits of upper and lower bounding functions as x goes to 0. Okay, let's do that first. If you insert 0 here, what is the limit of this function as x goes to 0? Please tell me. If you insert 0 here, what is the result? You can also type to chatbot. We need to communicate during these online lectures. Otherwise, it is kind of, I am totally alone here and I don't like it. So please tell me, what is the limit of this function as x goes to 0? Thank you, Murat. It is 1. And what is the limit of this upper bounding function as x goes to 0? Since it is a constant function, it takes always the value 1, no matter towards which value you approach, it is also 1. So you see, as it is desired here, the lower bounding and upper bounding functions have the same limit. Then, the middle function, then by sandwich theorem, the middle function has to have the same limit, okay? So the conclusion here is the middle function, which is this one, 2 times cosine x as x goes to 0, has to have the same limit to by sandwich theorem. Okay, this is how you use it. Not that difficult. You only need to check the limits of upper and lower bounding functions. If they are the same, then middle function has to have the same limit too. Okay, sandwich theorem. Any questions? Okay, let me move on then. So next exercise, again, it includes sine 1 over x. We already discussed the behavior of this function above, as you remember. Okay, let me draw it again to here. It takes values between +1 and -1, and it oscillates. Then around origin, infinitely many oscillations, then it goes back to normal. Here it behaves like crazy. There is an around origin, it oscillates too fast. Around origin f of x equals sine 1 over x oscillates infinitely many times. It's kind of a crazy function. We call this behavior as wild oscillation. Then, what happens if you multiply this function with square root of x? This is what we need to consider here. It affects the graph. Okay, if you multiply by square root of x, you will first draw square root of x function and minus of it. You know, this is the minus of it. And then we will draw the same graph that we drew here for sine 1 over x to obtain the graph of square root of x times sine 1 over x, okay? The same graph applies here, but it has to move between these two curves. It cannot oscillate between plus and minus 1 anymore. It will oscillate between these two curves. It cannot it cannot exceed square root of x and minus square root of x. It does the same behavior between these two curves, okay? That's why we draw the graph of square root of x times this sine 1 over x. This function has this graph which does the same behavior between square root of x and minus square root of x function, okay? So I think you got the idea. Now we are ready to answer the questions here for part A. By the way, okay, for part A, we want to find limit of this function as x goes to 0 from right, okay? We need to consider this part, right? What do you think? What is the limit? If it is not bounded by square root of x and minus square root of x, which is the case here, no bound. It oscillates infinitely many times between -1 and +1. That's why here, limit of this function as x goes to 0 does not exist because of this fact. It oscillates too fast, infinitely many times, so that there is no unique number towards which your function approaches. But what if we force our function to squeeze like this around origin? You see, it is not oscillating between +1 and -1 anymore because of this upper and lower bound. The values are kind of forced towards 0, right? And that's why around origin now, the situation is different than this. No oscillation between +-1 anymore because by this curve and this curve, we forced our graph to squeeze towards the value 0, right? That's why, what is the result of this limit? What do you think? Okay, the geometric explanation. I did the geometric explanation where this function is g of x, square root of x times sine 1 over x. X goes to 0 from right. So what happens here? Okay, still there are infinitely many oscillations, but these oscillations has to move between this and this curve, and this curve pushes your graph towards origin. That's why this time the images are approaching to some unique number, which is 0, okay? So this time limit exists. Unlike this case, this time limit exists and it is 0. Okay, this is the geometrical explanation of it, but you can also obtain this limit algebraically by using sandwich theorem. How you would do that? So you know the upper bound and lower bound for this function. This is the middle function. What is the upper bound for it? It is square root of x. What is the lower bound for it? It is minus square root of x. And you want to compute the limit as x goes to 0 from right? As x goes to 0 from right. If you insert 0 inside the square root, of course, you have to approach from right because for negative values, square root is not defined. So both upper and lower bounding functions goes to 0 as x goes to 0 from right. Then the middle function done by sandwich theorem, the middle function, which is this one, has to have the same limit too as 0. Okay, so you can obtain the same result also by using sandwich theorem. This is by using sandwich theorem, or geometrically you can discuss it like that as I explained to you. Okay, any questions about part A?
No.
Is it clear enough?
Yes, teacher.
Okay, now we will look at the limit from left, not right, but left. Look at the left side of origin. Is there any graph here? There is no graph over this part, on the left part, which means that your function is not defined for x less than 0, which means if you want to search for the limit as x goes to 0 from left, you will directly conclude that it does not exist because there is even no function there. So this does not exist as g of x is not defined for x less than 0. So you cannot talk about the limit. And part C is about the overall limit, not from right, not from left, but the actual limit. You will compare these two results. You see, one-sided limits are not the same. That's why the overall limit is what? Does not exist too, as one-sided limits are not the same as the finite real number. Okay, so that's it. This example is also a nice one. So let me show you from the beginning on so that you can go through it to see if you have any questions or not. Any questions? Okay, then.
No, teacher, thank you.
Okay, then this leads us to the final part. This is the content of the last lecture video uploaded on OneDrive. So this rule is a very useful rule while we computing limits algebraically. I will solve these two questions and I will stop then. So this is a very famous rule, as I said. I won't prove it here because of the time limitation. I only say that you can use this rule or the reversed version of it. You can use it also in this form. This is also one. So I just reverse the function, right? Okay, how you use it? Let me show you in 28. So I will be solving this. The question is, limit as x goes to 0, 6x squared cotangent x and cosecant x to x. Okay, first of all, we need to understand whether this is an indeterminate form or it directly gives us the result. To understand this, we need to rewrite trigonometric expressions in a nicer way, like cotangent x is in fact cosine x over sine x. Cosecant x is 1 over, who remembers the trigonometric identity for cosecant 2x? 1 over sine 2x, okay? You need to know such trigonometric expressions. Okay, now I am ready to trying to insert x goes to 0. If x goes to 0, what do we have? 6x squared is 0, cosine 0 is 1, sine 0 is 0, 1 over 0. Okay, what is 1 over 0? It is infinite. We mentioned that above. 1 over 0 is infinite. Infinity times infinity is infinite. So we end up with this expression now. 0 times infinite. What is that? As you remember, I put that
indeterminate form.
Exactly. This is one of the indeterminate forms that we listed in the first lecture. Indeterminate form. So what to do? If you end up with an indeterminate form, this means that you need to work harder to find the hidden result inside this indeterminate form. So our aim is to use this rule or this rule. Let's see if we can use it. Okay, I will write 6 squared. I will decompose it as 3x times 2x. Why do I decompose it like this? You will see. Okay, x goes to 0. I will send 2x to here. Why I am sending it to here? Because, I want to use this rule. If I have 2x over sine 2x, I can use this rule. That's why I'm sending 2x to here. And 3x remains there. Okay, 3x over, I have sine x here, cosine x is there, and I have sine 2x, and I send 2x here. You see, this is exactly the form that I write here. X over sine x as x goes to 0, which should be 1. This is a rule. You can directly use it. And also this part goes to 1 because of the same rule. This means that you may have coefficients in front of x, 2, 5, 100, it doesn't matter. But what matters is these coefficients should be the same, and 2x, these two same expressions should go to 0 as x goes to 0, which is the case. So you can directly use your rule, okay? And if you put this goes to 1, this goes to 1, you end up with a very simple expression, which is 3 cosine x. So the result is obvious now. It is just inserting 0 for x, 3 cosine 0. Cosine 0 is 1, as you know, so the result is 3. Okay? So, as you can see, using this rule or this rule in the reversed version is very useful in some algebraic limit computations. Any questions now?
No, teacher, it is clear.
Okay, then we can continue with the next one, which is also a famous standard example in calculus course. So the question is, limit 1 over cosine theta over sine 2 theta as theta goes to 0. Was it like that? Yeah, 1 over cosine theta, sine 2 theta, theta goes to 0. Okay, let's try to understand what happens if we insert theta equals 0. Cosine 0 is 1, 1 minus 1 is 0, sine 0 is 0. You see, we end up with an indeterminate form again. Indeterminate form. So we need to invent something here to get rid of this indeterminate form. But it is not that obvious in this case. I accept that. What I will do in a second is not that obvious, but once you see it, you won't forget it. As I said, this is a very famous standard type of example. So I will show it now, then you will never forget it what to do. We will multiply and divide by the conjugate of this expression, and it will help us to resolve everything. You see, I just changed this sign minus to plus. It is the conjugate of it. I multiplied and divide. This is a very famous question. Whenever you see 1 minus cosine theta and it leads you to an indeterminate form, this is the standard thing to do. Multiply and divide by this expression. Okay, then how this helps us? What happens next? This is now a minus b, a plus b form. So we can easily multiply them quickly, like a square minus b square. And then I will write denominator as it is without changing anything. Okay, so now we have this. What is 1 minus cosine square in terms of sine? Can you tell me an expression in terms of sine for this part?
Sine square.
Exactly. This is sine square theta. Thank you for your contribution. So we have sine square theta, sine 2 theta, and 1 plus cosine theta. Okay, next. There is a trigonometric identity for this thing, which is called as the half angle formula. Do you remember it? This is the same as writing 2 times sine theta cosine theta. This is called as the half angle formula. Then what we have, limit as theta goes to 0, sine square theta 2 times sine theta cosine theta 1 plus cosine theta. You see, this is the simplification that we search for. Okay, now we get rid of 0 over 0 by simplifying sine theta from numerator and denominator. Then what we have just sine theta in the numerator, and we have 2 times cosine theta 1 plus cosine theta at the denominator. Now I think we are safe to insert theta goes to 0 because we already simplified the zeros that cause us the indeterminate form like that. Okay, insert. Sine 0 is what? Okay, I'm just inserting 0 here. Sine 0 is 0. Cosine 0 is 1. 1 plus 1. Again, cosine 0 is 1. So the result is 0 over 4, which is... What is 0 over 4?
0.
It is 0. Okay, so your result is 0. Here, the crucial thing that helps us to invent something is to multiply and divide by the conjugate of that expression. And this happens a lot, like in Calculus 1 course. If you have 1 minus cosine theta and it leads you to an indeterminate form like that, 0 over 0, this is the standard way of processing that example. Okay? So, any questions about this solution? If no questions, I stop here and I stop recording. Thank you for your attention.